Morning all. Hope everybody doing good. In this video, I am going to explain about the magnetic circuits. Okay, magnetic circuits. The name itself is saying that the which deals with the magnets. Okay, generally we know about the magnets. What we know, magnets is having the two poles, north pole and south pole. Same poles will repel, and opposite poles will attract. Okay, that is for the permanent magnets. Okay, in the case of electrical engineering, we are studying for the magnetic circuits. Why? Because of we are doing the electromagnets. That is, whenever current flowing through that one, the material is acts like as a magnet. Okay, those kind of things we are calling as a electromagnets. So before going to start about all those things, there need some basic terminologies which will useful to discuss about this subject. Okay, the first one is magnetic flux. Okay, so magnetic flux, it's the lines of force created by the magnetic circuit. Okay, the unit is Weber. Okay, so WB we can represent with the WB. The second one is flux density. Always we know that density means per area. Okay, so flux density means flux per area. So that is what I discussed. So which is represented with the letter P. Okay, so magnetic flux is represented with phi, and magnetic flux density is represented with B. So B equals to flux per area. So the units will always, the units of the flux is Webers. Area of units is square meters. We also term the units of flux density as Tesla. Okay, and then the next one is magnetomotive force. That is represented with the letter F. Okay, the force which drives to tend the magnetic flux through the magnetic circuit. Okay, that is similar like as EMF, electromotive force. That is the force which is moved the electron. In this case, the force which drives the magnetic flux, which is represented with MMF. Okay, magnetomotive force. Simply we are writing as MMF. So it is defined as the number of turns into the current flowing through that one. That is number of turns. N I am representing and current NI. So the number of turns is represented with the turns, and units for the amperes is ampere. So the units for the MMF is ampere turns. The next term is magnetic field strength, which is represented with the letter H. Okay, the name itself, it is the strength, means how much it is going to cover. Okay, that is the magnetomotive force per meter length of magnetic circuit. That is MMF by length. Okay, we know NI is the MMF by length. Okay, so ampere turns per meter. Permeability, which is represented with the letter mu. Okay, the property of magnetic material which indicates the ability of magnetic circuit carry the magnetic flux. It is which will be differs for the different materials. So in this case, I mean we are using the magnetic materials as a copper, and there are many materials. For that one, we are going to calculate the permeability. Permeability is also defined as ratio of flux density to the magnetizing strength. Okay, we are representing flux density as a B and magnetic field strength as a H. So mu is become as a mu equals to B by H. So the magnetic flux units are permeability units are Henry per meter. Okay, we know that the in our earlier studies we discussed about the permeability is defined as a two things. It consists of two things, that is absolute permeability and relative permeability. The absolute permeability is defined as a 4 pi into 10 power minus 7. The relative permeability is depends upon the material which we are going to use. Okay, the relative permeability of the air is 1, and the reluctance, which is represented with the S. Okay, reluctance is the term which opposes the flow of magnetic flux. Okay, because the same thing which we discussed in the resistance in electrical circuits. Okay, which opposes the flow of electrons is the resistance, which opposes the flow of flux is reluctance. Okay, so for the to do the derivation for the reluctance, we know that the flux from flux density, flux equals to B into A, we can write, and the definition of MMF is N into I, or else we can write it as a H into L. Why? Because H equals to Ni by L. We can write Ni as a MMF. So HL, we can write HL as a MMF. Okay, and then from B, magnetic flux density B equals to mu H. From the definition of permeability, we can write B as a mu H. Okay. So from these three, we are going to find out. I am writing flux per force. Okay. So the flux is flux by mmf, B into A. The flux is defined as B into A, and Fy defined as H into L. And we know that the mu is a mu H. Okay. So I am writing mu H. Mu H. So from the numerator H and the denominator H will gets cancelled, and I am expanding the mu, that is mu naught into mu r into A by L. Okay. So from that one, flux equals to mu naught mu r A by L into F. Okay. Always flux phi equals to, why? Because I am relating the electrical terms. Okay. Flux is electrical terminology is in magnetic circuits. Flux in electrical terminology, flux is relates with the current. In the mmf, which relates the emf. Reluctance, which relates the resistance. So always I equals to V by R. So flux equals to mmf by reluctance. So F by S. Okay. So I am writing S value as L by mu naught mu r A. Okay. S equals to L by mu naught mu r A. So the units for the reluctance is mmf by magnetic flux. mmf units are ampere turns. Magnetic flux units are Webers. So reluctance can be represented with ampere turns per Weber. Okay. And if we consider a magnetic circuit, so I compare with the electrical circuit. Okay. So Ni is the mmf. Okay. That is your voltage source. This is your magnetic flux which is flowing through the circuit. That is your current. Okay. The opposition offered by the magnetic flux we are calling as a reluctance in the magnetic circuits, resistance in the electrical circuits. That is what I am representing over here. The similarities of the electrical and magnetic circuits are EMF is represented with the volt in electrical circuit and mmf in ampere turns. Current in amperes, flux in Webers. The same nature. Okay. Resistance is represented with ohms, and magnetic circuits we are represented with the reluctance ampere per Webers. Okay. Next, current density ampere per meter square, flux density Tesla or Weber per meter square. In this case, conductivity in the magnetic circuits we are calling as a permeability. There are some differences between the electrical and the magnetic circuits. In the case of an electrical circuit, current is actually flows. Okay. But in the case of magnetic circuit, flux is created but it does not flow. Okay. And in electrical circuit, closed path must. Okay. It always current is always flows in closed path. But in the case of a magnetic circuit, the flux will flows in either closed or else open also. Okay. Those things are represented over in a tabular column. Okay. So the path traced in the electrical circuit, path traced by the current is called the electrical circuit. In this case, path traced by the magnetic flux is called by the magnetic circuit. EMF is the driving force, mmf is the driving force. The current I in the electrical circuit measured in amperes, their flux is measured in Webers. The flow of electrons decides the current in conductor. The number of magnetic lines of force decides the flux. Resistance is opposed to the flow of current, and the reluctance opposed to the flow of magnetic flux. In the case of a resistance in electrical circuits, rho L by A. As we derived the reluctance is derived as L by A. That is the directly rho. Rho is the conductivity. In this case, permeability. That is 1 by mu naught mu r. Okay. Next, the current is defined as EMF by resistance. In the case of a flux is defined as mmf by reluctance. The current density is current per ampere, current per area. Flux density is flux per area. The conductance is 1 by resistance, and the permeance is 1 by reluctance. Kirchhoff current and voltage laws applicable to electrical circuit. Kirchhoff mmf law and flux law. mmf means voltage, flux means current, is applicable for the magnetic circuit. Hope you understood these ones. Okay. So be safe, guys. Thank you. Have a nice day.